Hello students, welcome you all. In my previous lecture of pericyclic reactions, I told you about the main features of pericyclic reactions and the brief of classification of pericyclic reactions. For example, electrocyclic reactions, cycloaddition reactions, sigmatropic reactions, group transfer reactions and chelotropic reactions. Okay, now before starting the this electrocyclic reactions, the detail of electrocyclic reactions, we should know the construction of pi molecular orbital diagrams. So how we can construct the pi molecular orbital diagram for the simplest system like ethene system which contain a pi bond, and some other systems like conjugated systems like butadiene which also contains the 2 pi bond, hexatriene or cyclooctatetraene, and some other odd carbon systems like allylic cations or some allylic systems. Allylic systems may be 3 carbon allylic systems, 5 carbon allylic systems, 7 carbon allylic systems, like this. Now, so first of all, I will tell you the simplest molecular orbital diagram for the ethene. So how we can construct the simplest diagram for this ethene. So before starting this pi molecular orbital diagram for ethene, so I will take the simplest molecular orbital diagram for hydrogen molecule. So we have seen the molecular orbital diagrams for the hydrogen molecule in our junior classes, +2 classes. So if you will see here, then how we draw it. So we take 2 atomic orbitals of hydrogen atom and 2 atomic orbitals of hydrogen atom, that is 1s orbital of one hydrogen atom and 1s orbital of the 1s atomic orbital of another hydrogen atom. So these 2 atomic orbitals, they combine in a constructive way or in a destructive way. So if they combine, then we get 2 molecular orbitals. So 2 atomic orbitals of hydrogen atom, they combine to give you 2 molecular orbitals, and one is called as the, so this is molecular orbitals and these are the atomic orbitals, and this is the atomic orbital of hydrogen atom. So they combine to give the 2 molecular orbital, and one is called as the bonding molecular orbital, which is the lower molecular orbital or stable molecular orbital, and another one is called as the anti-bonding molecular orbital. Okay, so here if you see, this one electron is present in this 1s orbital, and here also one of the electron is present in this 1s orbital. So if we want to fill the molecular orbital, then we will apply the Hund's rule. So by Hund's rule, we will fill the 2 electrons that would be filled in this bonding molecular orbital first. Okay, so what we have seen, when 2 atomic orbital combine, then they are giving you the same number of molecular orbital, that is 2. 2 atomic orbitals combine to give the 2 molecular orbitals. So this is one of the main point for the construction of the molecular orbitals. So if you see some of the characteristics for some of the rules for constructing the pi molecular orbital diagram, one of the rule that number of atomic orbital combined, that is equal to the number of molecular orbitals formed. So number of atomic orbitals combined is equal to number of molecular orbitals formed. Okay, so this is one of the rule. Now second rule, what this second rule says, that out of two molecular orbitals, as you can see, one is the bonding or another is the anti-bonding, or you can say half is the bonding and half will be the anti-bonding molecular orbital. So out of total number of molecular orbitals, formed, half is bonding molecular orbital and half is anti-bonding molecular orbital. Okay, so this is the two main rules that you have seen. So this is not the pi molecular orbital diagram. This is the sigma molecular orbital diagram, because in hydrogen molecule you will see the sigma bond is present in a hydrogen molecule. That's why you will see the sigma molecular orbital diagram. I have drawn here the sigma molecular orbital diagram. But in pericyclic reactions, we are concerned with the pi molecular orbital diagram, not the sigma molecular orbital diagram. So first we will draw the molecular orbital diagram for the ethene system, and we will then see some more rules for the construction of pi molecular orbital diagram. So let me draw first the pi molecular orbital diagram for the ethene system. So how we can draw? So if you will see the ethene system, then this ethene system, it has 2 pi bond. Okay, and these pi bond, they will overlap sideways, overlap between these two p orbitals. 2 p orbitals take place, and we will have the ethene system. Then we will get the ethene system. So I have drawn the p orbital of this this ethene. Okay, so if we want to draw the pi molecular orbital diagram, and since it has, this is the pi bond, and one of the bond is the sigma bond. So here we are only concerned with the molecular orbital diagram for this pi system. Okay, only we are not concerned with the molecular orbital for the sigma bond or sigma orbitals. Okay, so if we want to draw, then how we will draw? So for this, what we can see, the diagram is like this. Simplest diagram. So this 2p orbital, they can combine in two way. Either they can combine, constructive overlap can occur between this 2p orbital, or the destructive overlapping can occur between these two orbitals. Okay, so this is the simplest diagram for the this ethene system or 2 carbon system. So this is your bonding molecular orbital, and this is our anti-bonding molecular orbital, and we can name it, suppose we can name it psi1, and this is your psi2. So in this case, if you will see, then total number of nodes, if you will find for these 2 molecular orbitals, then node will be equal to nodes. How many nodes are present in psi1? There is 0 node. Okay, 0 node, because this plus plus, this is giving this is the constructive overlap. So number of node present is the 0, and here the number of node present is 1. So there is a anti-bonding interaction. So this is the bonding molecular orbital, and the interaction you see, this is the bonding interaction, and if you will see here, then this interaction is the anti-bonding interaction you will see. So that's why there one node is present over here. So one node is present in the psi2. Okay, so psi1 has 0 node and psi2 has 1 node. Now if you will see the other things, or we can say here how many bonding interaction is there. If I see, this is the bonding interaction. So bonding interaction here the bonding interaction, one bonding interaction in psi 1, and whereas here bonding interaction is 0. So number of bonding interaction in psi 1 is 1, and whereas bonding interaction in case of psi 2 is 0. Next thing, what about the anti-bonding interaction? Anti-bonding interaction, ABI, I am writing ABI, and ABI stands for here anti-bonding interaction. So anti-bonding interaction is 0, and bonding interaction is here, how much bonding interaction? Anti-bonding interaction, one anti-bonding interaction, as there one node is present over here, so one anti-bonding interaction is there. Okay, so this is, and same thing, same such type of thing we will also see for the other pi molecular orbitals diagram for the conjugated systems like butadiene or hexatriene or octatetraene, like this. Now I will also tell you the symmetries in these pi molecular orbitals. So if you will see the symmetry in pericyclic reactions, mainly in electrocyclic reactions, we are only concerned with two type of symmetry elements. So we have read symmetries element, for example, this mirror plane symmetry, C2 symmetry, and this SNS symmetry, or this inversion I symmetry. So in pericyclic reactions, we are mainly concerned with two type of symmetry elements. One is the mirror plane symmetry and another is the C2 symmetry. So here, so let's see mirror plane symmetry, that is denoted by sigma here. If you will see mirror plane symmetry in this case, then this psi 1, if you will see, suppose I pass one of the mirror plane in between these two p orbitals, suppose I pass mirror plane, then the in front of plus you will find plus, and I should also write here minus, and here minus, here I should write minus, and here I should write plus. Now if you will see the symmetry mirror plane, so psi 1 is symmetric with respect to the mirror plane. Okay, so and if you will see the psi 2, if we pass mirror plane here, if we have passed the mirror plane, then this is not symmetric with respect to the mirror plane. So if you will put a mirror here, then in front of plus you will not find the same image, you will not find the plus, you will find the minus, you will see the minus over here. So that's why it is anti-symmetric with respect to the mirror plane. So I will write here, it is symmetric with respect to mirror plane, it is anti-symmetric with respect to the mirror plane. So now let me understand you with the help of this model. So suppose this is the model here, and this is the ethene system. If you can see, this is the ethene system, and here this is the ethene system plus plus. So this green balls, this represents plus plus, and this yellow balls, this represents minus minus. Now if you will pass a mirror plane from here, then in front of green ball you will see the green ball, and in front of this yellow ball you will see the yellow ball. So this is the mirror plane. Suppose this is the mirror plane. So that's why we can say that this psi 1 is symmetric with respect to the mirror plane. Whereas if you will see the psi 2, then suppose this is the psi 2, this is our psi 2, and now whether this is symmetric with respect to the mirror plane, if I will pass a mirror here, then you will see in front of this green ball you will not find the green ball, you will find the yellow ball. Okay, so that's why this is not symmetric with respect to the mirror. So and that's why I have written, and this is anti-symmetric, psi 2 is anti-symmetric with respect to the mirror, and this psi 1 is symmetric with respect to the mirror plane. In the same way, suppose I write the symmetry with respect to the C2. Another symmetry element is C2. That is, what is C2? If I rotate if I rotate any diagram by 180 degree, then whether we will get the same diagram after rotation. If I get the same diagram after rotation, if I get the same figure after rotation by 180 degree, then that is symmetric with respect to the C2. That's, or we can say that has the C2 element, that has the C2 symmetry. So now let's see, if I rotate this one, and that is psi 1, if psi 1 is rotated by 180 degree, suppose this is our axis, and through this axis I rotate it by 180 degree, then what will happen? What will happen if I rotate it by 180 degree? Then this minus will go at this place, okay, and this minus will go at this place. It means we are not getting the same or molecular orbital after rotating by 180 degree. Now let me understand you with the help of this model. If you see this model, if I rotate it by 180 degree, okay, then what you will see? What you will see, I am rotating it by 180 degree, and let me rotate it like this. So if you will see, then what we have seen, we are not getting the same molecular orbital. So that's why this is not symmetric with respect to the, this C2. We should not rotate it like this. We should not rotate it like this. It should not be rotated like this. How we should rotate it? I will rotate it by 180 degree. Means this point will come over here. This point will come over here. So like this. So I am rotating it by 180 degree, and after rotation you will not find the same molecular orbital after rotation. We will not find the psi 1. So if I find the psi 1, it means it is symmetric with respect to the C2. So after rotation by this 180 degree, this thing, if I rotate it like this, you will not find the same psi 1. So that's why I should write here, this psi 1 is anti-symmetric with respect to C2. This psi 1 is anti-symmetric with respect to C2. Now if you will see psi 2, then whether this psi 2 is symmetric with respect to C2 or not, for this, suppose I have one of the axis, and through this axis I rotate this one by 180 degree. After rotation, what you will find? After rotation, you will see that this plus will go over this plus, minus will go over this minus. It means we are getting the same molecular orbital after rotating by 180 degree. That's why this is symmetric with respect to C2. Now let me understand you with the help of this model. Now this is plus, this is psi 2, this is psi 2, this is plus, this is minus, this is plus, this is minus. Now let me rotate it by 180 degree. So if I rotate it by 180 degree, then what you will see? Now, so this will come over here, this will go over here. So if I rotate it by 180 degree like this, after rotation, what you will find? So at plus, plus is coming, at minus, minus is coming. So firstly it was like this, plus was at this end, minus was at this end. So after rotation by 180 degree, you will see the plus is at the same position, minus is at the same position. It means this is symmetric with respect to the C2. So that's why. So these are some important symmetry elements that we should consider while drawing the pi molecular orbital diagram, or while we will discuss the electrocyclic reactions or this cycle addition reactions. Okay, so this is the simplest molecular orbital diagram for the ethene system. Now let me draw the pi molecular orbital diagram for the butadiene. Okay. Now, so what other rules that we can write? What you have seen? So these are the two rules when we draw the pi molecular orbital diagram. Another rule, what I told you, number of node in psi 1 is 0, and number of node in psi 2 is 1. So this is the number of node that I told you. It means psi 1 has 0 node, psi 2 has 1 node. In this way, you will see psi n. So for psi n system, for psi n molecular orbital, number of node that you will see later on in other diagram, for psi n, the number of node that will be psi n minus 1. So this rule you will see in other molecular orbital diagrams also. So third rule that I can write here, for psi n molecular orbital, for psi n molecular orbital, number of nodes will be psi n minus 1. So suppose if you are asked to tell what are the number of nodes for the fifth molecular orbital, then you will say number of node that would be 4. What would be the number of node for 8th molecular orbital? What would be the number of node for psi 8? You will see, you will tell this is number of node is 7, that is 8 minus 1. So this rule you will see in other molecular orbital diagrams also. Okay, now what you have seen, bonding and anti-bonding interaction. Here number of bonding interaction is 0 for psi 1. Okay, number of bonding interaction is 1, and for psi 2 it is 0, and for psi 3 the 1 and then 0. Okay, and in the same way the anti-bonding interaction, here anti-bonding interaction is 1 and this has 0. In this way you will see, for suppose I write for butadiene, in this same rule that you will see for the butadiene. So I will tell you. Now in the same way, what about this mirror plane symmetry and this C2? So mirror plane symmetry for first molecular orbital diagram, it will start with S. For second molecular orbital, then A. For third, it will S. For fourth, it will A, and so on. Means S, A, S, A, S, A. And for C2, it starts with A, and then come with S, and then again you will see A, again S, like this. It means the sigma for sigma mirror plane, that is mirror plane or sigma symmetry. So start with S and writing A, then S, A and S like this. For C2 we should start with A, and after that we will write S and then A and then S and so on. So same thing that will follow for other diagrams also. Okay, so another thing that you will see, first for odd molecular orbital, if you will see, always for odd molecular orbitals, the end orbital, here only two orbitals are present over here. So for odd molecular orbitals, end orbital will have the same sign, that is positive sign. For even molecular orbitals, psi 2 is even, psi 2 is even. So for even molecular orbitals, end orbital will have the opposite sign, that is plus minus, plus minus. So I am writing the rule, then you will see, you will understand the same rule when I will draw the next molecular orbital diagram of butadiene. So what I should write here, odd molecular orbitals, like odd molecular orbitals, for odd molecular orbitals like psi 1, psi 3, psi 5 and so on, the end orbitals have same sign. Okay, and for even molecular orbitals like psi 2, psi 4 and so on, the end orbitals opposite sign. So let me draw the molecular orbital diagram for the butadiene. Then you will understand these rules much more clearly. So how we can draw the molecular orbital diagram for the butadiene? Okay, this butadiene so this is our butadiene, or we can write it in this way also. So this is one of the p orbital, next one, and next one. So these two p orbital, they will combine to give this one pi bond, or this two p orbital can combine to give this pi bond. So here number of atomic orbital combined, number of, or we can say p orbitals combined. How much p orbital will combine? 4 p orbitals will combine. And how much molecular orbitals should form? 4. Number of molecular orbitals formed is equal to 4. So number of atomic orbital combined, this is equal to the number of molecular orbitals formed. Okay, so now let me draw the molecular orbital diagram for the butadiene. So if I draw it, then you will see this is our I may write it as a pi 1, then second, this is pi 2, third, pi 3, and fourth, pi 4. Okay, now I should give the sign. So what I told you, number of nodes, if you will see the number of nodes, then this psi 1 should has 0 node, psi 2 should have 1 node, this should have 2 node, and this should have 3 nodes. Okay, so how? It means the 0 can only come when all these have the sign positive. So this is positive sign, this is positive, 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 negative, negative, negative. Okay. Now for this, number of node is 1. So the first node that should always be passed through the center. This is the first node which should pass through the center. If we have one node, it means that should pass through the center. Okay, so nodes should be such that distribution should be symmetric. If you are giving the nodes over here, then distribution of nodes, that should be symmetric. Now third, so it means what sign that we should give? Half plus and half minus. Okay, what I have told you, for odd molecular orbital, the end orbital have the same sign. This is the odd one. So end orbital, that is this end and this end have the same sign, plus plus. Okay, I have not written the rule for this middle orbitals. I am only telling you about the end orbital. So for first, and that is the odd molecular orbital, the end orbital should have the same sign. Okay. Now this is the even molecular orbital. For even molecular orbital, what I have written, the end orbital should have the opposite sign. So as you can see, this and this are the end orbital, and this is having plus sign, this is having minus sign. So end orbital is having the opposite sign. But total number of node for pi 2, that should be 1. So only one node. So one node that can be drawn, that should always be passed through the center. Now side pi 3 is again, it is again the odd molecular orbital, and for odd molecular orbital, the end orbital should have the and orbital should have the same sign. So plus, 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 plus. Now how many nodes it should have? It should have, so let me write the, I can write the this sign also. So how many nodes it should have? It should have 2 nodes. This should have 2 nodes, means what I have told you, the next rule for psi n molecular orbital, the number of nodes will be psi n minus 1. That should be psi n minus 1. Okay. So for pi 3, number of nodes is 2. This is the third molecular orbital, so number of nodes will be 2. So how can we give the node over here? So I should give the 2 node, and the distribution of node, that should be symmetric. So no doubt the first node that should be passed from here, and another node that should be passed from here. Okay, these are the 2 nodes. Now, so again we can, so if this is plus, then that should be minus, and this should also be minus, because this is the anti-bonding interaction. One of the node is present over here. If this has plus, this should be minus. Okay, minus, minus, and this should have plus. This is plus, this is minus, this is a minus. In the same way, if you will see the fourth molecular orbital is the even molecular orbital, and the end orbital should have the opposite sign. So let me write the sign over here. This is plus and this is your minus. This is minus, this is plus. Now number of node, that is number of node is 3, or number of node is odd. It means one node that should always be passed through the center, and other two node has only this possibility that can be passed from here or from here. Okay, so if it is plus, then that should be minus. If it is minus, because one node is present, it should be plus, like this, and this is plus, this is minus. Okay, so also if you will see the number of interactions, if you will see the bonding interaction, so how many bonding interaction you can see over here? So what I told you for bonding interaction, here the bonding interaction is 3, plus plus, this is one of the bonding interaction, this is another bonding plus plus, this is another bonding plus plus. So bonding interaction is 3, and you can write itself. If it is 3, then psi 2, that will be 2, it will be 1, it would be 0. So how 2? If you will see number of bonding interaction, this is 2 only, you will see only 2 bonding interaction. This is one bonding interaction, another bonding interaction, this is another bonding interaction. Okay, here bonding interaction is 1. So how you can see bonding interaction? The bonding interaction is only between these 2 orbitals, this one. So only one bonding interaction. Here you will not see any bonding interaction. This is plus, this is minus, this is plus, this is minus. Bonding interaction means same sign. The bonding interaction will take place between the same sign. So same sign here, this is same sign, same sign, same sign. So 3 here, 2 here, only one same sign is present in the neighbor, and here you will see no bonding interaction. In the same way, if you want to write the anti-bonding interaction, here you should start with 0 and then 1, 2 and 3, like this. Okay, so 0, 1, 2, 3. So if you will see, the number of anti-bonding interaction is 0, because all have the same sign. All p orbitals have the same sign. That's why the anti-bonding interaction is 0. Here, if you will see, anti-bonding interaction is only between these two middle orbitals, that is plus minus. Only one anti-bonding interaction, and this is between these two. Only one anti-bonding interaction. Sorry. And if you will see here, anti-bonding interaction is between this first and the second, plus minus, and third and fourth. So two anti-bonding interaction, 1 and 2. And if you will see here, for fourth, number of anti-bonding interaction is 3. So this is 1, this is 2, and this is 3. Plus minus, minus plus, plus minus, like this. 3 anti-bonding interactions. Okay. So hope you are understood. So notes for pi 1 0, for pi 2 1, for pi 3 third, it means it will decrease by 1, that is 2, for fourth 3, like this. Now if you will see the symmetry, then how we can write the symmetry for it. So suppose two symmetry, that we are concerned with the two symmetry. So mirror plane symmetry and C2 symmetry. So what I told you in my last construction of this ethene molecular orbital, C2, if you will see this sigma, if you will pass the mirror plane in the middle, then you will see in front of plus you will find plus, and in front of plus you will find plus. So if you will pass the mirror plane over here, then you will find the mirror plane, the symmetric, it is symmetric with respect to the mirror plane. That's why this is symmetric with respect to sigma. This molecular orbital is antisymmetric. If you start with S, then you can write itself S, A, and so on, like this. And if you will see C2, whether this is symmetric with respect to C2? No. Suppose if one of the axis is there, and if you rotate it by 180 degree, and what you will see, in place of plus, after rotating by 180 degree, this corner will come over here, this corner will go over here. So at plus, at this place you will find minus, whereas at this place this minus will come over here. So this is not symmetric with respect to C2, this is anti-symmetric with respect to C2. This is symmetric, this is anti-symmetric, this is symmetric. So let me understand you with the help of this model. If you will see this model, then you will see that whether this is your pi 1, this is pi 1, and if you will pass the mirror plane like this, then in front of green, in front of, or you can say plus, all plus are there, in front of plus, all plus are there, in front of minus, all minus are there. Okay, now this is about the sigma, Now if you will see the C2, whether this is symmetric with respect to C2 or not, for this I should rotate it by 180 degree. Now if I will rotate it by 180 degree, this end will go over here, this end will go over here, and I will rotate it like this. So in place of green ball, yellow ball is coming. So it means we are not getting the C2, we are not getting the same molecular orbitals after rotating it by 180 degree. That's why this is anti-symmetric with respect to C2. Now let me see for this pi 2. So if you will see for pi 2, what kind of pi 2 you will see? This is the pi 2. This is our pi 2. 2 positive here and 2 negative. 2 positive, 2 negative. Whether this is symmetric with respect to sigma. Now if you will pass the mirror plane over here, then what you will see, in front of green ball you will find the yellow ball, in front of green ball you will find the yellow ball. That's why this is anti-symmetric with respect to C2 sigma. What about C2? This is symmetric with respect to C2. Now let me rotate it by 180 degree. So suppose I rotate it by 180 degree. Let me rotate, whether at place of green is coming, whether at yellow place yellow is coming. So let me rotate it by 180 degree, means this end will come over here, this end will go over here. So this is the pi molecular orbital diagram for the butadiene. Now this butadiene, the molecular orbital for this butadiene, it can be understood in another way. So how it can be understood? So this can be considered as the combination of two ethene system. This pi molecular orbital diagram for butadiene, you will see this is the one of the ethene system, and this is the another this ethene system. So if I combine the two ethene system, then we get the butadiene. If I combine two ethene system, then we get the butadiene. So how we can understand it? So after combination, we should get the same molecular orbitals. So let me draw the this pi molecular orbital of butadiene in another way. So how? When we combine the molecular orbital diagram of two ethene system, then we should get the butadiene molecular orbitals. So two ethene system, these are the two ethene system. Okay, so suppose I draw it in this way. This is our psi1. Psi1 means plus, plus, minus, minus. And this is the second molecular orbital of ethene. As you know, this is plus and minus. This is minus, this is plus. This is psi2. This is psi1, this is psi2. So all of you, I have given you the molecular orbital diagram for the ethene. So this is ethene. Okay. Now this can combine. This psi1 can combine in a two-way. Psi1 can combine in a two-way. Here I am also writing this ethene, molecular orbitals of ethene. This is plus, minus, plus, minus. This is psi1 and this is our psi2. This is our psi2. Plus, minus, minus, plus. Okay. So this is ethene. This is ethene. Okay. Now I should write the molecular orbitals of the butadiene. After combining two ethene system, we should get the same molecular orbital like here. So if I draw it, then suppose this is first one, this is our second one, third molecular orbital that I have written, this is suppose pi1, this is pi2, this is pi3, and this is our pi4. So 4 p orbitals, 1, 2, 3, 4, 1, 2, 3, 4, and so on. Okay. So now, this psi1, now I should give the sign. Now psi1 can combine in a two-way. One is the constructive way, another is the destructive way. So how? So suppose in a constructive way, plus, 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 plus. Okay. Number of node is 0. Now in a second, number of node is 1. So number of node is 1. So how they may combine in another way, that is a destructive way, plus, plus, and then minus, minus. So plus, plus, and then in a destructive way, minus, minus. Okay. So here minus, minus, plus, plus. Okay. So how many nodes? Here you will see one node is present over here. Here 0 node, here 1 node is present. Now pi3 can be found out by the combination of these two, either constructive overlap or destructive overlap. Number of nodes that should be only 2 nodes that should be present. So how we can get the 2 node? So for this plus, 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 minus, this is ethene, and we should get the 2 node, and plus, minus, here 1 node, here 1 node, as you can see. So here you will see this should be in a destructive way, that here it will combine, so that this minus, minus comes over here, minus, plus, plus, minus. Okay. So first, in a constructive way, you can see the middle orbital have the same sign. Here also the middle orbitals having the same sign when we are adding in a constructive manner. In a destructive manner, the middle orbital is having the different sign, plus, minus. Now Now here again this can be combined, plus minus, minus plus. So how we will combine plus minus, plus minus. So number of nodes is 3. 1, 2, 3. So we can consider the pi molecular orbital of butadiene as the combination of two ethene system. So if you see here, then the both are having the same molecular orbital. Either we can follow this rule or we can follow this rule. So better to follow this rule, and other rules naturally, automatically you will see the other rules will come over here. Okay, so in my next lecture I will tell you the pi molecular orbital diagram for the hexatriene and octatetraene. Okay, thank you.